So hello guys and welcome to a new video of deep learning papers implemented. Today we're gonna be explaining one of the most important and famous deep learning papers and like key figure in generative AI, one of the most cited really, which is denoising diffusion probabilistic models. And this paper actually like it kickstarted it all. Um, it was published in 2020 by three researchers at Berkeley, and people at the time just skimmed past it. And because I mean the paper was dense, it was full of variational calculus, and it looked like another incremental generative modeling paper. However, every image generator that you use actually, in a way or another, uses this paper ever since. And the actual idea behind the paper is actually very simple. Like it can be implemented in nine lines of code, as we'll see later on. However, the difficulty is understanding the simplicity and the justification for this simplicity. So yeah, this was a very brief introduction to it. Um, so, uh, what's really nice is that this paper is built on stuff we already explained before. So it has the same objective as the variational autoencoder. So if you already watched the variational autoencoder episode, you already will know most of the stuff here. Diffusion, it uses the same objective. So we're trying to generate images from noise. It uses the same loss, the elbow, and we already really dived into the elbow, but we'll re-dive through it. And it also uses the same reparameterization trick. So this is the biggest win here. We also did the UNet, and it turns out to be literally the same network. So it's a network that will approximate the noise, as we'll see later on, is actually the UNet. So yeah, if you haven't already seen the UNet video, go ahead and check it out. Attention shows up briefly, just as a detail. If you haven't seen the attention video, it's fine. So basically, we're trying to approximate a probabilistic model P of X of faces. Okay, so we're trying to get the probability distribution of faces. If it had an expression, the expression would be too complicated because this probabilistic distribution is actually has, as we discussed in previous videos, has 49k variables, and variables are really like not correlated. So you'll have really different faces, and the idea is that you should think of every possible picture of given size. It lives in this of a face. It lives in this probabilistic distribution. So real faces are the tiny island in the middle, and so to get this expression, we can't get it. So we do the that's the idea behind generative modeling, to be able to generate, let's say in this case, a face. However, you can use generative modeling to generate any like maybe not just faces. You can generate pictures of cats, of locations, um, and it's actually pretty hard. And we discussed already how variational autoencoders did it. Now we're gonna discuss how diffusion models do it. So, um, so the idea is actually very simple. We start with an image. We start introducing noise and destroying it. Then we have to learn how to undo this destruction. So again, we start with an image, let's say my image. We start adding noise, 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 noise. At some point, it becomes unreadable, and then we will train a neural network to learn how to undo that, as we'll see later on. Okay, so the generation becomes iterative denoising. So we added noise, so it's two processes, noisening and denoisening. So generation basically becomes denoisening. Uh, and so nobody teaches the model, listen, sit down and imagine how a face looks like. You teach the model, here's noise, learn how to denoise it. Okay, so that's the idea behind the paper. And basically we have two processes. Okay, we have from going from left to right, we have the noisening process, the forward process, where basically we're adding noise. Uh, we write it as Q, just a notation. We start with a real image. We add a little noise. We get x1. So we started with x0. We added a little noise. We got x1. Then we add a little bit more of noise. We get x2, which is a bit more blurry than x1. Then we add a bit of more noise. We get x3, and so on. We do it like 1,000 times. At x1000, it depends how much you want, you'll have a really, really noisy image. Okay, that's unreadable actually. This is a forward process. No learning happens here. It has no parameters, no neural networks. Basically, we're just adding noise bit by bit. However, um, going from right to left is is a difficult task. And here, as you can see, we note it as p theta of xt minus 1 given xn. So, uh, going from a normal image, let's say of a cat, to a really, really blurry one uh, is um, is relatively easy. However, going from the really blurry image to the normal image of the cat is what is hard. Okay, it's a reverse process. Uh, as you can see, we have a subscript theta. And the set basically just means that it has learnable parameters, that it's a neural net. It will be approximated by a neural network. All right. So destruction is free. The forward process over here, the Q, the forward process, it has no parameters. We're basically destroying the image. However, the blue process, the backward process, has parameters, and it's neural networks that we're trying to learn. Um, so um, if we want to compare it to variational autoencoders, basically in variational autoencoders we had an encoder and it mapped an image to a latent space, and a decoder that uh, that basically sampled from the latent space and mapped back. And the hard part was part that took the whole video we did about variational autoencoders was the encoder. And in the variational autoencoder, the encoder, so we had an encoder and a decoder, the encoder was also a learned neural network, and we had to train it with the decoder. Now, if we look at the diffusion, so here we have encoder is learned. In the diffusion, basically diffusion is same as variational autoencoder. However, the encoder is just fixed noise. All right. So encoder is still here. It is a forward process. However, it is not learned. It's just adding Gaussian noise 1,000 times. Uh, and also, just like in variational autoencoders, after we train the network, we um, we don't use the encoder in inference. So if we're trying to generate an image, we don't use an encoder. So steps go from 1 to 1,000. Latent is the same size as the image. So if we want to do a comparison, latent in variational autoencoder was smaller. Here it's the same size as an image. And the decoder is also a neural network. And the objective is still the elbow. So yeah, that's it. Um, So the takeaways that I want you to understand from this slide is that a diffusion model is basically a variational autoencoder whose encoder got removed and replaced with a fixed recipe. Everything painful about variational autoencoders, from learning a good encoder to finding a good latent space, to blurry samples, all of it goes away. Now, we're gonna talk about the most important parameter in the forward process, which is beta. Beta basically answers one question, which is how much do you want me to destroy the image? If we have beta equal to 0, we get the same image. We denoise it at nothing. If we get beta equal to 0.02, close to 0 but not entirely 0, we get uh, just a bit blurred image. When we have beta equal to 0.5, we got a half destroyed image, and at beta equal to 1, basically the image is Gaussian noise. So beta basically answers the question, how much do you want me to destroy this image? And the paper uses 0.02. So yeah, this is about beta. And now a question, which is why do we uh, blur it just a tiny bit? So in the forward process, as I said at the beginning, we're going from an initial image to complete noise. Why do we do it 1,000 times, introducing just a bit of noise every time? Why don't we just go in one step from a normal image to complete noise? And this is actually an interview question I once got asked in a deep learning interview. And basically, the answer is simple. It's because in the backward process, we're making the network estimate um, estimate the image before. So we give it a blurry image, and we ask it how was the image before we blurred it out. If we give it complete noise and we tell it give me the initial image, it's way harder. The network will require too much parameters to do it. However, if we ask it go from if we teach the network undo the blurring from step 99 to step 100, it's actually easy, because between step 99 and step 100 we have just a bit of noise, so undoing it is easy for the network. However, from step if we go just in one go, if we teach the network in one go from step 1 to step 1000, it's impossible. And this is an interview question, by the way, guys. So regarding how do we add noise, the obvious way is that we just add a bit of noise. So we start with x0. We calculate x1 is the image over here, as x0 plus some noise. So at every pixel, we draw a number between 0 and 1 following normal distribution, different for each pixel, and we multiply it by radical beta, uh, and we explained why. So uh, we don't add too much noise, and we get a bit blurrier image. Then x2 is calculated as x1 plus radical beta epsilon, the same. We just add, so we don't add the same number at every pixel. Be aware. Every pixel gets a number drawn between 0 and 1 using standard normal. Okay, and we keep doing it on and on, n times. In the paper, they chose n equal 1000, so we get xn is equal to x0 plus radical n beta epsilon. So every step is basically approximately as if we are at x1, as if we are sampling it from a normal distribution with mean the previous image and standard deviation beta I, which is beta multiplied by 1. If we stack n normal distributions, we'll get that xn is basically centered around x0, so it has mean x0 and has standard deviation n beta. If we replace the numbers in the paper, we get with n equal 1000 and beta equal to 0.02, the variance is 20. So the standard deviation is 4.5 radical variance. So every pixel is swinging by plus or minus 4.5, which is a lot. This is what we call exploding variance, and it was a problem which the paper authors had to solve. So the way they solved it is that uh, they multiplied each number, um, they multiplied each image by radical 1 minus beta. And because beta is close to 0.02, radical 1 minus beta is around 0.98. So basically, they just like it's very close to 1. So they shrank every image just a tiny bit. So what they did, okay, they started with an image, they shrank it a bit, then they added noise. And the reason why they did it is that before we got variance is equal, the standard deviation ended up being 4.5. When we do this at infinity, mathematically we can derive it, we'll get that the variance will become 1 at infinity. So the way to make it 1 and not face this problem of exploding variance where we have n beta is to shrink every time the image by radical 1 minus beta. So yeah, that's it. So the forward, basically at each step, we take an image, we shrink it by radical 1 minus beta, which is around 0.98, and we add a small noise, we add noise of around 0.02. If we do it 1000 times, we'll land at n01. Now, if we want to jump from step in the forward process, because as I said earlier, the forward process has no parameters. It's not a neural network. We are not learning it. So if we want to jump from x0 to xn, we can actually do it. Basically, we calculate xt, the final t is last step, as radical alpha bar t x0 plus radical 1 minus alpha bar t epsilon, and epsilon follows 0 and 0 1. And again, guys, epsilon is not one variable, okay? So it equals the number of pixels, so it's a matrix. Let's say we have an image 700 by 700. It's 700 by 700, 49k variables sampled from n01 added to each individual pixel. Now, what is alpha bar t, and what alpha bar t is just basically the multiplication of all the alphas, and the alpha is 1 minus beta. That's it. So let's say we have beta is equal to 0.02, 1 minus beta is 0.98, and basically alpha bar t is a multiplication of all the alphas. You're gonna ask me, why do we have a t subscript here? It's because we have what we call a scheduler. I'm not gonna dive into it now, I'm gonna explain it in the code, but basically we start changing the beta across time. So that's it. If we wanna see why, like why mathematically this is correct, as I said before, x2 is calculated as radical alpha 2 x1 plus radical 1 minus alpha 2 epsilon 2. You're gonna ask me, you're gonna say, no, no, we had radical 1 minus beta plus beta, but I just told you alpha is basically 1 minus beta. Okay, so it's just a change of variable. So I'm gonna go to slides before. Um, Radical 1 minus beta, it becomes radical alpha, and beta becomes radical 1 minus alpha. So x2 is radical alpha 2 x1 plus radical 1 minus alpha 2 epsilon 2, correct? Now, substitute x1. x1 is what? It's radical alpha 1 x0 plus radical 1 minus alpha 1 epsilon 1. And here we have no x1, so it stays the same. If we expand, we'll get radical alpha 2 alpha 1 x0 radical alpha 2 into 1 minus alpha 1 epsilon 1 plus radical 1 minus alpha 2 epsilon 2. However, epsilon 2 and epsilon 1 are both normal distributions, so they're the same actually. They're just epsilon, which is a standard normal. So we can unify, we can take them as common factor, epsilon, we get radical when we take as common factor, we can expand it. We'll get radical 1 minus alpha 1 alpha 2, and and yes, that's basically it. Alpha 1 alpha 2 is pi alpha from 1 to 2, and yeah, so and yeah, this is a part of expansion we got over here. So if we do it n times, here we'll get radical alpha 1 alpha 2 till alpha n x0 plus radical 1 minus alpha 1 alpha 2 till alpha n epsilon, which is basically the pi we substituted over here. So this is just a mathematical derivation. Um, so we already spoke about the forward process. Now we're gonna talk about the backward process. And as I explained earlier, forward was Q with no setup. Backward is a P with theta, which is just that it's a neural network which is parameterized. In the backward, we're trying to estimate the previous x, let's say x99, given a blurry x100. So given a blurry image, we're trying to unblur it a bit. And it's basically, we're trying to approximate a normal distribution with mean mu theta and standard deviation sigma. Now, by design, sigma, the variance is sigma square. Sigma square is fixed, so we fixed it. The entire learning problem is just learning how much the mean is. So, which will be estimated later on in the video with a neural network which takes as an input the time step t and the image xt. Now, uh, while training, we can cheat actually. So we have x0. We train the network to get x0 given a blurry image xt minus 1. However, after we finish training in inference, we start from pure noise, and from pure noise we try to generate an image. All right. Now, if you want to look at the forward process, in the forward process, we're trying to estimate x1 till xt, knowing x0. So basically, we're trying to get xt, the Gaussian noisy image, given x0, the normal perfect image. Basically, it's a multiplication of all of every step. So it's basically xt given x0. Xt is the blurry image. The blurry image given a normal image is the blurry image given the bit unblurry image before it, multiplied by the bit unblurry image before it, xt minus 1, given xt minus 2, blah blah blah, till we get q of x1 knowing x0. And as a notation, it's just a multiplication of it. The same can be said about the backward process. So p theta of x0 knowing xt is basically x0 knowing x1 multiplied by x1 knowing x2 multiplied by x2 knowing x3, blah blah blah, till we get um, till we get um, xt knowing xt minus 1 knowing xt. All right. And because we start from pure noise, we can factor out p set of xt. This is just a notation. So the forward process q of x1 till xt knowing x0 is has this notation, pi of xt knowing xt minus 1, and p theta of x0 uh, given xt has this notation, pi of p theta of xt minus 1 knowing xt, all multiplied by p theta of xt. Uh, basically we try to so now, okay, now we have a learning objective. The learning objective is we have a pure noisy image xt. We want to get a normal image x0. So we try, just like in the variational autoencoder video, we try to maximize log likelihood, which is equivalent, because in training we try to minimize, not maximize, to minimizing the negative log likelihood. So maximizing the log likelihood is equivalent to minimizing the negative log likelihood. Um, it's minimizing negative log of p seta of x0, and it's basically nothing. It's just how well did our model get an actual image given pure noise. And x0 can be written as so p seta of x0 is basically p seta of x0 till t multiplied by every integral possible. So I know this sounds a bit complicated, but I promise you not. Basically, here we have x0, our image, and here we have xt, and we're basically saying to calculate the log of p seta of x0, we have to walk every path imaginable from xt to x0. So let's say I have a noise, here I have an image of a cat, noise image of a cat. I have to walk every way that can takes me from the noise to the image of the cat, and it's actually infinite. This is intractable, so it's not possible. Okay, so each dashed line is one pass x0 could have taken. The integral sums over all of them, and we have infinite, so it's intractable. So we're gonna have to find another trick to do it. Okay, so one trick to do it is, if we go to the previous slide, we had the forward, we had the backward. Instead of going from the forward, we so instead of doing the log likelihood of the backward, we multiply and divide by the forward process q, and it's basically equivalent to multiplying by 1, because if we're multiplying and dividing by q of xt knowing x0, it's equivalent to multiplying by 1. And this basically becomes the expectation, because when you're doing an integral or summation over a probability multiplied by something, it becomes the expectation uh, under this probability. And because here we're multiplying by q of xt knowing x0, it becomes the expectation under the forward process. And using Jensen inequality, this this is less than or equal to when we inject the log 2 inside the equation. So it becomes less than or equal to the expectation under q of log p seta over q. And in the paper, uh, they continue. Maybe I can do a future video on it, but they start from here, they continue it, and they reach the elbow, which we the elbow expression which we had in the previous video. So I'm not gonna go into it because it's like 2 pages of math, but they start from here, and basically they reach um, the expression over. Let me find it over here. Okay, so I'm gonna go over it in a different video, maybe in the future, but not now, because it's variational calculus. Now, KL divergence, we already explained it in a previous video. Um, we explained divergence in a previous video. Basically, we're trying to um, measure the difference between two probabilistic distributions. And the expression is, if we have two distributions q and p, it's expectation under q of log q over p, and this is what we got at the end, the KL divergence. Um, so Basically, we explained in a different video. We spoke a lot about the KL divergence. Uh, so as we can see here, blue is Q, the true distribution. Red is P seta. What and our gas, they overlap, um, but the red one sits too far right and is too wide. KL puts a number on that mismatch. And the three properties of KL divergence is that it's zero when they are identical. It grows as they drift apart, but it's never negative. And yeah, that's it. Now, in practice, um, it's just basically the subtraction of the two means. So it's basically calculated as mean 1 minus mean 2 square over 2 standard deviation squared. And we saw it in the implementation of variational autoencoders. It was basically just subtracting two means. And why is that? That's basically because here we have P and here we have Q. Because they have the same standard deviation, they have the same widths, and they just have different centers. So to measure how far off they are, we can simply just subtract the means, and that's it. Again, we go back to the expression of the elbow. This is the expression of the elbow. So it's a KL divergence of of xt knowing x0 in comparison to p of xt. This has no parameters. The second one is uh, the last one is the log likelihood of x0 knowing x1, and because x1 and x0 are just consecutive, they are basically the same, so their log is very close to zero, so we don't use it in our gradient descent loss function. Same for the first one, because the first one has no parameters. As you can see, it depends on xt, and so it's like fixed. The second one, which is the KL divergence, the difference between Q of xt minus 1 knowing x0 and P seta of xt minus 1 knowing xt, is where the actual work is. And in practice, it's just the difference between the two means. So basically, our loss function will be just a mean squared error of the means. Now, if we wanna have the expression of the mean, this is it. In the paper, they derive it. It's 1 over radical alpha t, and alpha t is alpha, you remember, is 1 minus beta, into xt minus beta t over radical 1 minus alpha bar t, multiplied by epsilon 0 of xtt, and epsilon 0 is the noise. So, everything here is a constant. Xt is the image before. We have it as input. Alpha t is a constant, which is radical 1 minus beta t. Beta t is a constant. Alpha t bar is the multiplication of all alphas. So here we only have epsilon 0. So the idea is that the network uh, doesn't predict the previous image, given a blurry image, doesn't predict the image just before it. It predicts how much noise was added to make you. So instead of predicting pixel by pixel every image, it predicts pixel by pixel how much noise was added. And this is because of the reparameterization trick. Um, so basically, network job collapsed to just this question: which noise added you? So the target is now always unit variance and well scaled at every time step, and this made the network train so much better. And so pages of variational calculus in the paper collapse into what's shown over here. Basically, we just take an image, we pick a random timestamp, we draw noise, we add the noise, we ask the network how much noise got added. That's it. And then, because we have the actual noise, and because the network guessed the noise, we subtract the difference, and then we update the parameters of the network to have the network better predict the noise. And this is the loss function that produced every image generator you have ever used, even in video generation nowadays. Now, um, as I discussed earlier in earlier slides, the true elbow has three terms. The first one gets thrown away in the gradient descent. However, as a third term, let me show it to you over here. Um, how do I exit? So I guess it was. Uh, Sorry for that, guys. So the third term log p theta of x0 given x1, as I said earlier in the video, x0 and x1 are very close, so this number is really close to 0. So in the paper, they decided to just discard it. So the true elbow is over here, the lost simple is over here, and they measured the difference, and they were actually very close. So and so and actually it made the model perform better when they removed it. Um, and this is one of the key findings of the paper. Now, if you want to talk about the algorithm that they used, basically we grab a real image, okay? We pick random timestamp, we draw noise, we gradient descent, we do the gradient step on the squared error between the noise and the network's guess, and we have no discriminator here, no adversarial game like in GANs, just one mean squared error. And at each training exactly does one timestamp. So one timestamp, we go in the forward in one step, and we just teach the model at one timestamp how to undo the denoising. Now, um, in the sampling, so when I say sampling, I mean generation. We start from pure static Gaussian noise. We loop backward. We ask the network for the noise. So we sample noise. We subtract a fraction. We rescale. And then we add a little noise back in. Because if your network is already trained on denoising, we just make it denoise 1000 times. Okay, so we start from pure noise, okay, a pure noisy image. We tell the network do this 1000 times. 1000 times, estimate the noise, and because there's a formula that given the noise you can calculate the mean, and because the standard deviation is constant, basically we're getting the image. So um, So the last part I spoke about just now is what surprises everyone, because without it, this process is deterministic and not a generative process, and I spoke about that in the variational autoencoder video. And it collapses towards the average of everything the model has seen. Um, the injected randomness is what makes the process diverse. So I'm gonna talk about this in about the training loop in the video of implementation. However, it's basically just 9 lines of code. We get t, we get epsilon, we get xt, and xt is basically we make the network guess how much epsilon is, and we do a loss function model of xt, and because I told you the network takes t and takes the image and guesses the noise, and we do MSE, mean squared error, between the actual noise epsilon and model of xtt, which is the network's guess of how much epsilon is. Then we do gradient descent loss dot backward. And the difficulty of the paper was in the justification of this 9 lines of code. And that's why it has so much math in it. Now, the network, uh, it's basically, so the network that takes as input t and xt and guesses the noise is basically a unit. So it has skip connections. However, it just has one small difference. Um so UNet, as we spoke in a different video, it contracts down, it expands up, and it skips connections. The additions are in red over here. Network needs to know which time step it is on, because denoising at step 100 is different from denoising at step 300. So T becomes an input, and usually, as we spoke in attention is all you need video, T, to give time information, we usually use sinusoidal embedding, uh, the same positional encoding from the transformers video. And there's also self-attention at 16 by 16 resolution. Um, and it's basically just to give the model context on the relationship between the individual pixels. And yeah, that's it. So, uh, why does this need a thousand? This does not need 1,000 networks. Why do we use just one network? Because T is an input, not a different model. One function of two arguments sharing weights across every noise level, and sharing helps because neighboring time steps are almost the same problem. So we don't need 1,000 models. We need one model, and we just give T into it. Um, these are the results of the paper. Um and they tested it on CFAR 10 at the time, and I mean it was a bit slower than GANs. Uh, yeah. Uh, so here is just a small comparison with GANs, which I will talk about in the future. It's one forward pass. Here we have 1,000 forward passes. Here we have no latent space to interpolate in, and beta and sigma are schedule are guessed by hand. And next, after DDIM, after DDPM came DDIM, which decreased the number of steps. Then improved DDPM came, which learned the standard deviation as well. Then came classifier free guidance, and latent diffusion, and which was do all of this inside the variational autoencoder, and flow matching as well. Flow matching, I will implement it in a future video, perhaps, because it's what's used nowadays in video generation as well. But however, just a small word on flow matching. Flow matching is basically the same. We start from noise and we're trying to reach a non-noisy image. However, we start like doing like a flow where, let's say, the noise is like a vector. We start moving in space till we reach actual image. I will talk about it in a future video. It's equivalent to diffusion. However, it works better in practice. And if you want to summarize, so now let's say we're in an interview and someone asks you to explain to him in simple words diffusion. It's basically a variational autoencoder. The encoder is just noise. At every step, we have the next x, the next image is the initial image multiplied by radical alpha bar plus noise, which is scaled by radical 1 minus alpha bar. And this is lets you in the forward pass jump anywhere in time. Um, and the network is trying to predict the noise in the backward pass. And we have the actual noise, so we just subtract them. And the network is basically UNet that also takes as input the time and encodes it. And yeah, that's it. Thank you guys for watching. Perhaps my next video will be about ResNet, and I will be implementing as well in a future video a simple the diffusion model code, and I will be explaining flow matching in the future because it's very very important. If you have any questions, feel free to leave it in the comments or message me on LinkedIn, and I'll see you guys next time. Bye.